At the beginning of the 20th century, scientists believed they were on the verge of explaining the world completely. Under Newton's laws, every natural phenomenon seemed predictable, and physics looked almost complete. However, no one realized there was a hidden, unknown world that Newtonian mechanics could never reach. In the quantum world, bizarre and mysterious events were unfolding that we simply couldn't make sense of. In 1905, Albert Einstein shocked the scientific community when he explained the photoelectric effect, how electrons are ejected when light hits a metal surface. He proposed the idea of wave-particle duality. Light can behave both like a particle and like a wave. Sometimes light spreads out like a wave, and at other times it delivers energy like a stream of particles. The laws of classical physics they had trusted could no longer explain everything. In 1926, Erwin Schrödinger introduced a wave equation, now known as the Schrödinger equation, to describe the strange way particles seem to be spread out like waves over a region of space. This equation showed that a particle is not pinned to a single position, but can exist in a superposition of many possible states. It also provided a mathematical way to predict a particle's position and energy only in terms of probabilities. The equation became an essential key to understanding the quantum world, but even Schrödinger himself didn't truly know what it meant. What does the wave function actually represent? As quantum mechanics began to be studied in earnest, Niels Bohr and Werner Heisenberg proposed the Copenhagen interpretation, which says that a particle exists in a superposition of many states until it is observed, and that measurement forces it into one definite state. This interpretation soon sparked enormous controversy. At the center of it was Albert Einstein. Einstein could never accept this probabilistic view. He famously said, "God does not play dice." In 1935, Einstein and two fellow physicists, Boris Podolsky and Nathan Rosen, published the EPR paper, pointing to what they saw as fundamental limitations in quantum mechanics. Put simply, they were saying, if quantum mechanics is correct, then once two particles have become entangled, no matter how far apart they are, the instant one of them takes on a definite state, the other's state is fixed as well. Does that really make sense? In their picture, the distance between the two particles simply didn't matter. This phenomenon even seemed to go beyond the speed of light. Mocking this seemingly unreal behavior, Einstein called it spooky action at a distance. To him, this looked like a fatal flaw in quantum mechanics because it directly clashed with his belief that nature should be fundamentally predictable and deterministic. Ideas like probability and superposition appeared to him to be just a provisional interpretation, not a true description of reality. Einstein's jab about spooky action at a distance couldn't shake Bohr. He saw this strange behavior not as a flaw, but as the very core of quantum mechanics. Ironically, Schrödinger's cat went on to become the iconic metaphor for the uncertainty and superposition of quantum mechanics, and the bizarre effect once mocked as spooky action at a distance turned out to be one of the most mysterious and powerful features of quantum physics, what we now call quantum entanglement. The very questions that were meant to deny quantum mechanics ended up providing some of the strongest answers to what the quantum world is really like. The more they insisted, this is impossible, the more the quantum world seemed to answer, that's exactly what quantum mechanics is. In 1982, French physicist Alain Aspect conducted a historic experiment with entangled photons, directly observing the very spooky action at a distance that Einstein had so strongly criticized. The moment the state of the first photon was measured, the state of the other photon, located several meters away, was instantly determined. Scientists watched this unfold with their own eyes. The two photons were clearly bound together by an invisible connection. Quantum entanglement was no longer just a hypothesis or a topic of debate. It was a fundamental feature of our universe. Today, quantum entanglement lies at the heart of cutting-edge technologies like quantum cryptography and quantum computing. By harnessing the properties of entangled particles, we've begun to build virtually unbreakable, secure communication channels and perform computations that were once unimaginable. But even now, we still don't know why quantum entanglement happens at all. Science has only confirmed that this phenomenon is real, and we're still just learning how to turn its principles into technology. There was a time when many people, including Einstein himself, believed that quantum mechanics had to be wrong. Today, no one seriously makes that claim. Someday, just as when quantum mechanics first appeared, we may discover yet another law or phenomenon that sounds completely absurd. When that day comes, even as we examine it critically, we should remember the moment we first uncovered quantum entanglement. No matter how impossible it seems, it might simply be reality.